Okay, my name is Jason Northern, and we'll be looking at our milestone number 3 for my part of the project of charging your car and charging the grid. My portion of the project specifically focused on the power electronics, mostly on the rectifying portion of the circuit. The major tasks that were accomplished here in milestone 3 were building and testing a prototype for the power electronics. So here's a block diagram that just basically is a refresher of what I'm going to be covering here in my milestone. You can see we've got the 60 hertz rectifier there on the grid to coil power electronics, as well as we have a 7.3 kilohertz rectifier on the coil to grid power electronics. And then over on the car side, we have a coil to vehicle 7.3 kilohertz rectifier as well. So here's basically the circuit. As you can see, we use 4 IGBTs. We have a sinusoid on the left, our DC buses over on the right. With this circuit design, the 4 IGBTs are not operated at all. We're strictly using the anti-parallel diodes for the purpose of rectification. Using these 4 diodes, it creates a full wave rectifier. And we need to also have a large capacitance there, calculated to need to be around 10 millifarads or so in order to get the ripple we wanted. We ended up with a total of actually having 12.4 millifarads of capacitance. So we just needed to create a prototyping platform. You can see there we chose to do this using plexiglass, so we could have kind of a see-through work plane that we could be able to get underneath and fiddle with the wires, change the connections, that type of thing. We can also easily kind of swap out the components. The reason we needed to go this route is because we're working with high currents and large components that aren't going to just fit inside of a standard breadboard. As you can see, basically we just soldered on some 12 gauge wire onto the end of the leads to give us a connection point, and we did most of our connections just using wire nuts, and this worked adequately for our needs. So initially we decided we need to start with a low power test. We started using just a bench signal generator. The max output on those is about 10 volts peak to peak. Due to the high current draw, due to the high capacitors, when we actually tested this out in practice, it actually dropped that voltage to about 3 volts peak to peak, and we were able to successfully charge up the DC bus. And this was while the whole circuit was connected to the coils and the inverter was operating as well. When we did from that test. Then we also performed a low power test using Variac. The inverter was not in operation. We were just solely running the rectifier and the capacitors. Was all that was connected, and we used Variac to slowly turn it up until we got up to 20 volts VAC, and we saw that our DC bus charged to roughly 20 volts. Then we decided to move on to high power tests. Initially, we plugged the circuit into the wall. We just had a 15 amp breaker there protecting the circuit. Well, in addition to the 15 amp breaker, we also had some inrush current limiters. We had about 30 ohms of inrush current limiters. Unfortunately, what basically happened is those inrush current limiters, they're negative temperature coefficient thermistors. So as they heat up, the resistance goes down. And basically what happened is they heated up before those capacitors charged up enough to lower the inrush current to a manageable amount. And we ended up blowing out those inrush current limiters and exceeding their current capabilities, as well as burning up some of our diodes. So basically the better solution to this, rather than using inrush current limiter resistances as they heat up too quickly, would be to get some power resistors, resistors that can handle a few hundred watts, and switch those into the circuit initially to limit that inrush current, and then once we've got the circuit up and running in full operation, we can then pull those out of the circuit and just bypass those resistors. That would be the ideal solution. Due to time and financial constraints, we opted to, for the time being, to use a variac transformer. That way we can just slowly increase the voltage and monitor the current as we do so that we aren't putting in more current than what we can deal with in the components, and to be able to charge up those capacitors to a level before we connect a load. So here we have a video of us doing exactly that, doing a high power test with a variac. You can see we've got a voltmeter here, as well as an ammeter that measures current by measuring the flux. So we're measuring the input coming in through the input current going into the system to make sure that we keep that in a reasonable level, as well as monitoring the voltage there on the capacitor. And then at the end, we use a power resistor, 360 ohm, 100 watt resistor to just charge the capacitors. So as you can see here, we're slowly turning up the variac, and the voltage on the capacitor is increasing. We're keeping an eye there on the current, and as you can see, it never really goes above 100 milliamps. A couple times we brush it, but it doesn't really go over. Just taking it slow, making sure that we aren't pushing the circuit too hard. And our goal here is to get up to 170 volts. That being the full rectified, a fully rectified sine wave, 120 volt sine wave. As you can see there, we hit 170 volts, which is the peak value of a 120 volt sine wave. You can't see in this video, but the variac is aligned to 120 volts there. And here we switch it off and lower the voltage, and our capacitors are retaining that 170 volts fairly well. You can see it dips a little bit. And then now we're going to grab a power resistor here, connect it to the capacitors, and we can see we're able to safely drain those capacitors. All right, so some of the problems that we've encountered here with the rectifiers is first the inrush current. The method in which we solved this problem was using the variac. The real end solution for this problem would be to have resistors that we would initially have in the circuit during startup, and then we would switch those out during normal circuit operation after the initial startup. But we also had issues with burning up the diodes. We believe that the main problem here is that we had the collectors of the different IGBTs with their anti-parallel diodes shorting out through the heat sinks. So that was an issue, and we think that those shorts was causing problems with our diodes, because they tend to short out to have problems more at the lower powers than when we didn't really have any high power tests where we had issues with them. We usually found it during the low power tests and when we started up. And so we think that was probably the main issue. We did a better job separating the heat sinks and isolating them from each other, and that seemed to have solved the problem. And then another problem we have, which isn't directly related to the rectification, but we are also burning up gate drivers. We're not 100% sure as to what was causing this problem, but we're thinking it's something along the line of either the bootstrap capacitances. There's an issue there with those values, or the gate resistances are too small, and we're trying to push too much current to the gates too quickly, quicker than what those gate drivers can handle. So the overall efficiency of the rectifier was calculated to be 97.4%. That was just calculated based on the conduction losses of the diodes, as well as the reverse recovery losses of the diodes. That was a hand calculation we made. The heat sinks are needed due to those losses if we're operating at full power. However, we did not get around to measuring the efficiency with the entire system, as we had some other issues that we were still working on solving at the time, which issues still have yet to be solved. So, still some more work in getting this the whole system to work, so that we can measure the efficiency of the entire system and see what we can get out of it. But that's basically the work that we did for our third milestone. Thank you.